Okay, we're going to continue our modern physics unit talking about relativity. Last time we talked about Galilean relativity, which is that relativity that we normally see that all physics works in a non-inertial reference frames, uh, meaning that as long as it's not accelerating, then physics works as we would expect it to. We saw that there started to be, or I told you that there was a problem when we started to approach the speed of light. Physics equations started to not work. So that's where special relativity comes in. This didn't come about, though, until Einstein in the 1960s or so. Uh, he developed the idea of special relativity. And here, remember, we're just doing the basics, very, very basic. So special relativity. This is going to handle the speed of light issue. So first off, each law, remember all the laws we studied all year? Each law of physics works in all inertial reference frames. That should sound super familiar. Okay, physics works in inertial reference frames. Galilean relativity. So what did he do? Well, there's a second part of this. The speed of light in a vacuum is the same in all reference frames. So no matter where you see light, whether you're accelerating or not accelerating, the speed of light is going to remain the same. That's odd. So take that in for a second. I'll let y'all pause if you need to, but we're going to keep moving. Relativistic speed. This is a vocabulary word. Relativistic speed refers to an object traveling at very nearly almost the speed of light. Very nearly almost comes from Charlie is so cool like on YouTube. That's a phrase he uses when he talks about things traveling at nearly almost the speed of light. Uh, so if we're watching something and it's traveling very nearly almost the speed of light, then it's at a relativistic speed to us, and vice versa. We're at a relativistic speed to it if we consider the frame of reference to be the thing that's moving. So remember, we got those two frames of references right away. When something is traveling at relativistic speed, or very nearly almost the speed of light, four things are going to happen. And these are the four things, these predictions at relativistic speeds. So when we observe something happening at nearly the speed of light, this one, which I have the hardest time saying, and I'm not going to try and say it on camera. Well, I will. Simultaneity. Basically, what that says is we have two events that appear simultaneously at the same time in one frame of reference, but not simultaneous in another. So one example I've heard of this is, let's say we've got a boat and a trailer, and we're on a really fast river. Okay, not a trailer, a dock. And this dock has got a light that's going to light up when the front of the boat passes it, and and on the other side, when the back of the boat passes it. So we've got a dock here with a light and a light, and the boat. Top of the boat's like this, so you got the motor here. So when the front of the boat passes here, this lights up. When the back of the boat passes here, it lights up. So on from the dock's perspective, when the boat reaches there, it's as long as let me see if I got this right. Yeah, when the boat reaches there, it's as long as the thing, so it lights up at the same time. However, on the boat, this light's going to get to the boat faster than this light, so we see this light and then this light. So what happens in one frame of reference is the simultaneous lights, same time. The other frame of reference, one lights than the other. That's that idea. We'll see that more in the video here in the next video in just a second. Time. So when things are traveling at relativistic speeds to each other, time slows down. And we've seen this to a very, very, very minor degree. We've taken some very, very fast jet engines, jet planes, and we've taken atomic clocks. I believe the experiment had 8 atomic clocks, 4 they left in the hangar, 4 they put on the plane. The plane took off, flew as fast as it could, came back, and the ones that were flying were slower than the ones that were on in the hangar for our control. But I mean, we're talking fractions of a second. Something else that happens is length shortens, which I've got a whole idea on that, which we'll talk about just in a second. But so as you speed up, length shortens. Another thing that happens that mass increases. I was going to put greater, but let's put increases. That's better sounding. And I think all of that is related to E equals mc squared. We get energy that comes from mass times the speed of light squared. And so here's one idea that I had. When in the Bible it talks about Jesus as being light, what if it's more than it's just a symbol? What if he is light? Well, if he is traveling the speed of light, time slows down. Well, if this is approaching the speed of light, when you're at the speed of light, time would stop. And so you're outside of time and you're in all times. Length shortens. Well, if length shortens, you go at the speed of lights, then length would be 0 and you would be everywhere on omnipresent. Mass increases, you would have infinite mass, therefore you would have infinite energy, you'd have omnipotent power. There's something there. We might be stretching that analogy a little too far, but I like the idea that there's something possibly there. Now the problem with special relativity is when we start looking at that it's still got this restriction of inertial reference frames. So the problem with sorry, I can't talk and write at the same time. The problem with special relativity is acceleration, specifically the inertial reference frame. So if your reference frame is not sitting still or not moving at a constant speed, then there's some issues. But these are the interesting things that come up in special relativity. So when you're talking about very nearly almost the speed of light, you're talking about relativistic speeds. And 2 different frames of reference, one thing happens at the same time, the other thing happens one after the other. Time shortens, length shortens, and mass increases. So in this next video, in your lesson plans, I've included the link to the pole and barn experiment or thought experiment. It's where a runner is going to take a 20-foot pole and it's going to fit it into a 10-foot barn by traveling very nearly almost the speed of light. So watch that, ponder things. If you've got questions or you want to discuss things, give me a call or text or email and we will set up a time to discuss it. Maybe we need to have a Zoom meeting to just talk about different aspects of it. We can do that as well. So just get in touch with me, and for homework tomorrow, I just want you to write a paragraph summarizing Einstein's special relativity. Show me that you understand what we talked about today. Have a good day, guys.